Alright, well, welcome to our lecture video for section 5.4. This section we're going to continue with the concept of trying to determine whether or not a series converges or diverges. So just as a quick recap, section 5.1 was our introduction to infinite sequences, a necessary prerequisite to understanding infinite series, which is really the major thrust of chapter 5. Section 5.2 introduced infinite series. Section 5.3 was primarily about using the integral test to determine whether a series converges or diverges. And it turns out being able to determine whether a series converges or diverges plays a pretty big role in deciding whether or not it's useful to us. So we're actually going to devote quite a bit of time to that and learn to use several tests. We've already learned one, the integral test, and we've learned how to determine whether a couple of important classes of series are convergent or divergent, the p-series and the geometric series. And now, in section 5.4, we're going to learn how to build on that knowledge using a couple of theorems known as comparison tests. Alright, so here's our outline for section 5.4. In the previous section, we saw that we can sometimes determine that a series converges or diverges by using the integral test, and the idea there is that we compare the series to an improper integral. Okay. Sometimes it's possible to determine whether a series converges or diverges by comparing it with another series whose convergence or divergence is known. In fact, sometimes that's simpler. Okay, here's a good example of that. Here's our series. Our series is an infinite series whose nth term is 1 over n cubed plus 1. Now in the previous section, we determined whether or not a similar series was convergent or divergent. In fact, the only thing that was different was that it was an n squared. It was 1 over n squared plus 1. And we were able to determine whether or not that one converged or diverged by using the integral test. But the integral test would really give us problems here, because to apply the integral test we would need to be able to integrate 1 over x cubed plus 1. Now we had an integration formula from Calc 1 for 1 over x squared plus 1, so the integral test was a viable option. But I don't offhand know any integration formula for 1 over x cubed plus 1. So, I mean, that would be my first clue, just glancing at this, that the integral test may not be the best way to go on this one. But I'll tell you something else you can pick up right away. Okay, I see a 1 over n cubed in this problem. Now, there's also a plus 1, but if that wasn't there, this would be a p-series. Okay, and in fact it would be a p-series that would be convergent. Okay, we said last time that for any series where the nth term is 1 over n to a power, we used p for power, 1 over n to the p, if p is bigger than 1, series converges. So if I didn't have that plus 1 there, I would have a convergent p-series, and I would basically be able to just state that. This is a p-series, p is bigger than 1, ergo, it converges. Okay, the plus 1 makes it not a p-series, but I can still make a comparison to a p-series. Okay, here's the key thing. The plus 1 makes the denominator bigger, which actually serves to make the fraction smaller. If you think about that, I think you know that's true. 1/3 has a bigger denominator than 1/2, but it's a smaller quantity. So here's how we would make the argument. We would say 1 over n cubed plus 1 is less than 1 over n cubed for all values of n greater than or equal to 1. Now sometimes this part of the problem actually takes quite a bit of thought and maybe even some algebraic derivation. But in this case, it's really just something that's true by inspection. If the only difference between two fractions is that one has a larger denominator, then it must be smaller. In fact, I could really make a stronger statement. I could say 1 over n cubed plus 1 is strictly less than 1 over n cubed. But for the argument that I'm about to make, it would be good enough to say less than or equal to. Okay. Now remember, we used a capital S for partial sums. So let's think of it in terms of this. So for the nth, now a lot of times we'll use a capital N when we want to talk about a specific value of n, but we don't want to actually nail down what it is. So for the nth partial sum of our series where we have 1 over n cubed plus 1. Now remember, a partial sum is we just add up the first however many terms. So here big N would represent some number of terms. For the nth partial sum of this series, it must be less than the nth partial sum of the series where we would just have 1 over n cubed. Okay, and I think the argument's pretty easy to follow there. Okay, if every term of this series is bigger than the corresponding term of that series, then if I add up the first big N terms of the smaller series, that would have to be less than the first big N terms of the series with larger terms. Okay. But the partial sums, so I'll say it like this: the partial sums of my series where I just have 1 over n cubed are increasing. Why are they increasing? Well, they're all positive, so every time I add another term to get the next partial sum, it's got to get bigger. Okay, those partial sums are increasing and bounded. Okay, increasing. Well, let me say it like this: and they converge. Okay. Now, I know that they converge because the series whose nth term is 1 over n cubed is a convergent p-series. Okay, if the series converges, then its partial sums have to converge. That's what it means for a series to converge. And we know the series converges because of a p-series argument. Okay, so the partial sums are increasing, but they converge. Now, I don't know exactly what they converge to, but they converge to some number. So we'll just say and we'll call it S. Let S be the sum of the series 1 over n cubed, where again it's understood that n goes from 1 to infinity if we don't actually write those things in. So then S is an upper bound for, now I bet this is starting to feel like a long argument, and that's okay. Most of the arguments won't be quite this long. We're kind of doing this one from scratch. So S is an upper bound for the partial sums of the series where the nth term is 1 over n cubed. But we already said that those partial sums are bigger than the partial sums of the other series, which implies that S is an upper bound implies that S is an upper bound for the partial sums of the other series, the one where the nth term is 1 over n cubed plus 1. Okay, now what that does for us is it allows us to say, all right, if the partial sums of this series are bounded by whatever the sum of the B series is, but they're also increasing because the terms are also positive, then we can use the monotone convergence theorem to say, hey, this series has got to be convergent. So we'll say it like this. Since the terms of the series whose nth term is 1 over n cubed plus 1 are positive, the partial sums of this series are increasing Okay, the partial sums of this series are increasing. So now we've shown that the partial sums are increasing, but they're also bounded. So by the monotone convergence theorem, the partial sums of the series whose nth term is 1 over n cubed plus 1 converge. So the series itself converges, which is what we wanted to get at. Now, here were the crucial parts of that argument. Okay, crucial parts were we were able to establish pretty easily that the terms of this series were less than the terms of a series that we knew converged, but also the terms were positive. So those two things, the first thing told me that the partial sums would be bounded. The second thing, that all the terms are positive, tells me that the partial sums are convergent, that the partial sums are increasing. And then those two things together, that the partial sums are bounded and that they're increasing, tell me that it's convergent. Okay, so we don't have to reproduce quite all that reasoning every time. As long as we can ensure that those critical elements are met, we can use the theorem known as the comparison test on page 487. So let's have a quick look at the comparison test. Here's what the comparison test says. Okay, it says, now the idea is A sub n is the series that you're trying to figure something about. Okay, the series whose nth term is being represented as A sub n, that's a series that you're trying to decide, does it converge or diverge? But we've been able to figure out that for all values of n, A sub n is less than B sub n, but also greater than 0, where B sub n represents the nth term of some series that we already know converges. Okay, so the idea is that if we can show that the terms of our series are all between 0 and the terms of a series that we know converges, then we can conclude that our series whose nth term is A sub n also converges. Now I do want to highlight something right here. Okay, we need to be able to show that this is true for all n greater than some big N. So the idea is big N represents some number. It could be 10 or it could be 100. Okay, it could differ from one case to the other. But what they're saying is this has to be true for all the terms past a certain point. So it wouldn't have to be true for every single term. Okay, maybe it could be that a sub n is actually bigger than b sub n for the first 10 terms. But if we know that this relationship is true for all the terms past some point, then we can apply this theorem. Now there's a second part to the theorem. We'll talk about that part after we've done a few examples. Alright, so let's look at some examples where we can apply the comparison test. Okay, we're going to look at problem 202. The instructions say use the comparison test to determine whether the following series converge. And then down here in problem 202, what we're given is the series where n goes from 1 to infinity, and the nth term is sine squared n over n squared. Alright, now here's the thing that I notice first about this series. The thing that really jumps out at me is the n squared, and I'll tell you why. Okay, when I'm using comparison tests, I know that I need to be able to make a comparison to a series that I already know is convergent. Okay, or maybe later in other examples I'll be making a comparison to a series that I already know is divergent. So I'm looking for some basic classes of series that I already know some things about. Okay, the two big classes of series that we know about are p-series, which would have the form 1 over n to a power, and then also geometric series, where we would have a constant raised to a power with n in it. Now here the n's aren't in the powers, they're in the bases, so I don't think we're going to be able to make use of geometric series. But the fact that I see that n squared in the denominator makes me think, hey, because of that n squared there, I might be able to make a comparison with a p-series. Okay, now the p-series where the nth term is 1 over n squared is convergent. So I need to be able to make an argument that these terms here are smaller than the terms of the convergent p-series, 1 over n squared. But I also need to make an argument that they're positive in order to use my comparison test. Okay, here's a fact I'm going to use. Okay, this is something that you probably know. Okay, fact. Sine of n. Okay, this is just a fact from trigonometry. Okay, any output of the sine function has to be less than or equal to 1, but also greater than or equal to -1. Okay, so the absolute value of sine is between -1 and 1. Okay, that means that sine squared, okay, so sine squared n would have to be less than 1 squared, which implies that sine squared n is less than or equal to 1 for all n. Okay, but it's also the case that when you square something, it can't be negative. Also, because it is squared, sine squared n got to be greater than or equal to 0. Okay, so if I take sine squared n and divide it by n squared, since sine squared n has to be less than or equal to 1, I can say sine squared n over n squared has to be less than or equal to 1 over n squared, but I can also say that it's greater than or equal to 0. Okay, so there were really two conditions I had to check there. Okay, I had to check that my terms would be positive, but also that they would be less than the terms of a series that I know is convergent. Okay, so remember, anytime we use a theorem to draw a conclusion about convergence or divergence, we have to check to make sure that all the conditions are met. The conditions for using the comparison test are that the terms of the series are positive, but also less than the terms of a known convergent series. Now, I need to explicitly write something down here, something I've been saying but not writing. So I'll go ahead and say it now. Now, since the series whose nth term is 1 over n squared is a p-series with p greater than 1, it is convergent. I needed to explicitly say this because this is sort of the last part of the conditions for applying the comparison test. Okay, I needed to know that my nth term of my series was positive, but less than the nth term of a series that's convergent, and I need to explain how I know that this series here is convergent. Okay, it should be obvious, but when you're writing up a proof, you're stating all your reasoning. Now we've shown that all the conditions of applying the comparison test are met. So the next stage of writing a proof is you say what test you're using if you haven't already. Okay, so by the comparison test, okay, so that's the second thing. First thing was show that we could use the test. Now state what test we're using. And then the last thing is your conclusion. State your conclusion. So by the comparison test, our series from n equals 1 to infinity of sine squared n over n squared is convergent. Okay, now ultimately that's our answer, but all of this write-up was the work. Okay, so if this was a test problem, I really wouldn't want to just see convergent or divergent unless I tell you that. Sometimes I might say on a test problem, state whether the series is convergent or divergent, but proof isn't needed. Okay, but unless I tell you proof isn't needed, you need to explain your reasoning. Okay, it's like showing your work. That's what showing your work means for these kind of problems. Alright, let's have a look at another problem in the book. Alright, here's our next example out of the book. The directions are still the same. We're still going to use the comparison test to try to determine whether this infinite series is convergent or divergent. Now, I picked this one because at first glance it looks like it's a lot more complicated than the ones we've done already, but it's actually pretty similar in principle. Okay, and I wanted to help you kind of cut through the mess and see the key things to help you decide what to do with this one. First things first, notice that the n's are showing up in bases, not in powers. Okay, that's a pretty good clue that we're probably going to make a p-series comparison. Okay, as opposed to a geometric series comparison. Now, if I was seeing n's in the powers and constants in the bases, I would make the opposite conclusion. Okay, now, here's the next thing. Obviously, this would have to be simplified to make a comparison to a p-series. Having multiple terms either in the numerator or in the denominator complicates things. Okay, but you should immediately start thinking, what if I didn't have multiple terms? And in particular, you should focus on the highest degree terms. Okay, now when I look at my highest degree term in the bottom, I see an n to the fourth, but I know that we're taking a cube root of the n to the fourth, so I really want to think in terms of sort of a net degree. The net degree of the bottom is not 4, it's actually 4/3. Okay, so here my net degree in the bottom is 4/3. In the top, my net degree, now I mean this is, I'm making this term up, net degree, but this is kind of how I think through these problems. I see a power of 1 but a root of 4, so that's really n to the 1/4. So my net degree is 1/4. Now, I want to think in terms of the difference of the degrees. Okay, 4/3 is really 1 1/3. So the difference of these degrees, it's going to be just a little bit more than 1. Not a lot more. The difference would be like 1 1/12. But the key thing is, it's more than 1. Okay, if the difference in the degrees is more than 1, then this series is going to act like a p-series whose degree is more than 1, so it should be convergent. Okay, but I've got to figure out what to compare it to. Okay, now here's how I can think through that. Since I believe that this series is convergent, I want to show that its nth term is less than the nth term of a convergent p-series. So I'm going to do something to change it, to simplify it, that makes it bigger, to try to get it to be a p-series. Okay, for sake of comparison. Okay, I'm gonna start with what I have. 4th root of n over the 3rd root of n to the 4 plus n to the 2. Okay, now remember, I want to come up with a p-series that's bigger than this. So I want to make a change that makes it bigger. Here's the change I'm going to make. I'm going to whack out that n squared. Okay, when I whack out that n squared, it makes the denominator smaller, and that makes the fraction bigger. So if I write almost the same thing, but I just leave out that n squared, now I've made the fraction bigger, so I can put one of these in there. In fact, really, I could say it's strictly greater than, but that's good enough. Okay, I just need to be able to say that this is greater than or equal to that. And now, believe it or not, that's my p-series. If I can get it down to one n term on the top and one n term on the bottom, then I'm pretty much there. I just need to simplify. So that's n to the 1/4 over n to the 4/3. So I guess I need a common denominator there. I'm going to use the rule that says, hey, when you're dividing and you have like bases, you can subtract the powers. Looks like a common denominator would be 12. So I'll say that's n to the 3/12 over, and multiply top and bottom by 4. That'd be n to the 16/12. Now I can subtract. 16/12 minus 3/12 is 13/12. And since the bigger power is in the bottom, that's where n will be left. N to the 13/12. Now 13/12 is not a lot bigger than 1, but it is bigger than 1. Okay, so now I'm ready to make my argument. Okay, so let me see. What's my argument here? 4th root of n over cube root of n to the 4th plus n squared is less than or equal to 1 over n to the 13/12. Okay. And the series whose nth term is 1 over n to the 13/12. Making sure I'm writing that twelfths, not halves, is a convergent p-series. Now there is one more detail that I have to attend to. Okay, I now want to use the comparison test to draw a conclusion, but there was one more condition. Okay, the condition was that my terms were negative. Now I have something on my side here. You know what? I made a little mistake in copying. That 2 should have been an n squared. Okay, the thing that's on my side is that n is greater than or equal to 1. Okay, we had that working for us. So I'll say since n is greater than or equal to 1, um, since n is greater than or equal to 1, fourth root of n and cube root of n to the fourth plus n squared are positive. So the fourth root of n over the third root of n to the fourth plus n squared is greater than or equal to 0. Okay, I wouldn't necessarily expect much of an argument here. Okay, it's kind of obvious that since n is positive, this expression would have to be positive, but that does need to be acknowledged. And I want to see you acknowledge it, even if you just kind of stated it without argument, even if you just said, and also since fourth root of n over cube root of n to the fourth plus n squared is greater than or equal to 0. I mean, sometimes it is okay to just say something is obvious, but you still need to acknowledge it because it's a condition of using the test. Okay? And we need to make sure all the conditions have been met. And so you kind of have to check them off in writing. One condition is that the terms are less than the terms of a known convergent series. So you have to include the algebraic argument if it's not immediately obvious. And in this case, I don't think it's immediately obvious. You kind of have to work through all that. But algebraic argument that the terms are less than the terms of a known convergent series. Okay. Explain how you know that it's known, because it's a p series. Okay, and we can look at the value of p if it's written in the correct form. Also, need to confirm that the terms are all positive. And now we're ready to say what test we're using and what our conclusion is. So, by the comparison test, and I'll capitalize it since it's the name of a theorem. By the comparison test, our series where n goes from 1 to infinity, and the nth term is given by the fourth root of n over the third root of n to the 4 plus n to the 2, is convergent. And again, this write-up, as I've shown it here, this is meant to be a model for you of what I'm looking for on homework and also on exams. Alright, well, let me see. I think I've got another one here on the outline, so let's have a look at that. Alright, so I'm still working on the list of problems that are at the bottom of page 1 of the outline. This problem was not actually in the book, but I wanted to get in a problem of this type at this point in time. Okay, there are some kind of like this in the book, but I wanted a specific one to get at a specific thing here. Still doing the same thing. We're still using the comparison test to try to decide whether a series is convergent or divergent. Okay. Now, when I look at this one, I'm again thinking, alright, can I make a comparison to a series whose convergence would be known? Which is typically going to mean either comparing to a p series or a geometric series. Now, in the previous examples, n was in the base and constants were in the power. That would tell you you're comparing to p series. But in this example, we've got constants in the base and n in the power. That would tell you to make a comparison to a geometric series. Now, to figure out what geometric series to compare to, I'm going to do what I did before. I'm going to start simplifying, but I'm going to try to simplify in ways that, as I make these changes, they make the fraction bigger. And I'll tell you why. Okay, there's other cases where you would intentionally simplify in a way that makes the fraction smaller. But let me tell you what I'm picking up on that tells me make it bigger. Okay, the minus 1 and the plus 1 are really kind of extraneous. They don't change the nature of the problem very much. The parts that really drive the nature of the problem are the 2 to the n and the 3 to the n. Okay, those are what make it like a geometric series. So if I home in on those, 2 to the n over 3 to the n could be simplified to 2/3 to the n. 2/3 to the n is a geometric series with an r value that's less than 1. Now remember, geometric series are kind of opposite of p-series. With p-series, if p is bigger than 1, that tells you convergent. But with geometric series, if the r value is less than 1, that's what tells you convergent. So I'm thinking this is kind of like a convergent geometric series. So I want to show that the terms here are less than the terms of that convergent geometric series. Because if I can show that they're smaller than the terms of a series that I know is convergent, then I can use the comparison test. Alright, so I'm going to take my nth term of my series and I'm going to make changes. I'm intentionally going to make changes that make the fraction bigger. My first change is going to be, I'm going to drop this -1. When I drop the -1, that actually makes the numerator bigger, because if you don't subtract 1, you're bigger. But if you make the numerator bigger, that makes the fraction bigger. So if I drop the -1, that makes the fraction bigger by making the numerator bigger. Next, I'm going to drop this +1. Now dropping the +1 makes the denominator smaller, but making the denominator smaller also makes the fraction bigger. So this is less than or equal to 2 to the n over 3 to the n. And now I'm going to use the rule for exponents that says if you have something raised to a power divided by something else raised to the same power, you can take the first base and divide it by the second base and raise the whole thing to that power. Okay. Alright, so I've just shown that 2 to the n minus 1 over 3 to the n plus 1 is less than or equal to 2/3 n. Okay. Now, the series whose nth term is 2/3 to the n is a geometric series with an r value, r equals 2/3. Now, since the absolute value of 2/3 is less than 1, this geometric series converges. Alright, that's one of the things I have to check off to be able to use the comparison test. But the other thing I've got to check off is I've got to convince myself that my nth term is always positive, okay, or at least is positive past a certain point. It would actually be negative. It would be okay if a few terms were negative, as long as I knew that past a certain point it was always positive. Now, I'm again going to make use of the fact that n, not m, n is greater than 1. That implies that 2 to the n is greater than or equal to 2 to the 1. And that implies that 2 to the n minus 1 is greater than or equal to 1. Okay, that was the big thing I needed to take care of. Okay. If I hadn't had any subtractions, I could have pretty much just said, hey, because there's no subtraction, no negative signs, it's positive just obviously, and I wouldn't really need to make an argument. But because there's a subtraction, I need to kind of check and make sure. Okay, so since the numerator is greater than 1, I can say 2 to the n minus 1 over 3 to the n plus 1 is greater than or equal to 1 over 3 to the n plus 1. And that part I can say is clearly greater than 0 because there's no negatives anywhere in there. Alright, so that takes care of the other condition. I've shown that my terms are sandwiched between 0 and the terms of a convergent series. So now I can go ahead and state what test I'm using and state my conclusion. So, by the comparison test, my original series, where the nth term is 2 to the n minus 1 over 3 to the n plus 1, is convergent. And that's all there is for that problem. Now, I've got a couple more to do. I kind of want to show you some different things that can show up as we try to analyze these. So still kind of focusing on this convergence test, let's look at just a couple more in the book and then we'll change directions. Alright, let's look at problem 199 from the book. Still the same instructions. Okay, use the comparison test to show that the series is convergent or divergent. Okay. I wanted to do this problem because this one involves something we haven't really talked about yet. It involves this concept of factorial. It turns out that factorial is actually something that comes up a lot with infinite series. Okay, you might remember that I mentioned before that we're going to be using infinite series to build polynomial approximations of functions that are transcendental, which is what most naturally occurring functions are. And it turns out that when we start learning how to do that, we're going to see that the process of building those polynomial approximations will pretty much always give us series that have factorials in them, or very, very frequently. They're kind of built in from the design process. So, let me just remind you what a factorial means. Okay, reminder. So we'll say for n greater than or equal to 1, n factorial equals n times n minus 1 times n minus 2, and you keep decreasing by 1 until you get all the way back to 1. So the factorial of a number is really just the product of that number and all of the positive integers that are less than or equal to that number. So as an example, 5 factorial would be 5 times 4 times 3 times 2 times 1. So let me see, 5 times 4 is 20, times 3 is 60, times 2 is 120. Okay. Now, factorials do come up in series a lot. Okay. And sometimes they can really complicate the series. But in this particular example, we can use a little bit of knowledge of what factorials look like to simplify them. So let's focus on the nth term of this series. Okay, it's n factorial over n plus 2 factorial. So we just defined what n factorial would look like. It's n times n minus 1 times n minus 2 times n minus 3 all the way back. Keep multiplying until we get to 3 times 2 times 1. Now, n plus 2 factorial would be, so n plus 2 is our number. We'll start with that number, and then we go to the number that's 1 less than that number. So the thing that's 1 less than n plus 2 is n plus 1, and then the thing that's 1 less than n plus 1 is n, and then n minus 1, and then n minus 2, and then n minus 3, and then all the way back to 3 times 2 times 1. Now at first, I know it seems like there's a whole lot going on here, but you might have already picked up on the fact that there's also a whole lot of canceling we can do. We can cancel that n with that n, and that n minus 1 with that n minus 1, and that n minus 2 with that n minus 2, and in fact everything's going to cancel all the way back to 1, The only stuff that doesn't cancel was right here, the factor of n plus 2 and the factor of n plus 1. So, n factorial over n plus 2 factorial equals 1 over n squared. I'm sorry, I don't want to get ahead of myself. 1 over n plus 2 times n plus 1. Now, in this case, at this point, it would be useful to go ahead and multiply that out, because if I multiply it out, I get an n squared, and I guess I'm going to have a 3n and a plus 2. Okay, now here's the thing that jumps out to me, that n squared. Okay, that highest degree term in the denominator kind of tells me what I should expect this thing to act like. Okay, this nth term simplifies to 1 over n squared plus 3n plus 2, which is really pretty similar to 1 over n squared. And in fact, if I drop out the 2 and I drop out the 3n, both of those changes would make the denominator smaller, and that makes the fraction bigger. So now I can say that my nth term is less than or equal to the nth term of a convergent p-series. Okay, so n factorial over n plus 2 factorial is less than or equal to 1 over n squared, and the series whose nth term is 1 over n squared is, so here I'm just stating that which is obvious by inspection, okay, that this is a convergent p-series. So is a convergent p-series. Okay, so I've shown that one of the conditions of using the comparison test is met. I've explained why that is met, okay, because I've made a comparison showing that the terms are less than the terms of a convergent p-series. Now I also need to confirm that the terms are not negative, that they're greater than or equal to 0. Now, because there's no subtraction or negative signs floating around, I'm pretty much good. It's true just by inspection, but I still need to state it, just to confirm that all the conditions are met. Also, n factorial over n plus 2 factorial is greater than or equal to 0 for all n greater than or equal to 1. So, by the comparison test, our series, whose nth term is n factorial over n plus 2 factorial, is convergent. Alrighty. Alright. I want to do one more problem of this kind. All the problems we've done so far have been basically the same type, in that they were all convergent series, and for all of them it was possible to make the convergence argument using the comparison test. Okay, this is another one in that vein, but I'm showing you different things that can happen in terms of what you have to do to show that the comparison test applies. So, in problem 198, the nth term is 1 over n times the natural log of n, and all of that's squared in the denominator. Now notice this one's a little unusual in that they specifically tell us that n starts at 2. And that's actually necessary in this case, because if we let n start at 1, then we would have natural log of 1 in the denominator. But natural log of 1 is 0, and of course we can't have 0 in a denominator. So it's necessary that we be specific that this series is actually starting from n equals 2. So we definitely need to write that in here. Alright, well, now if I take my nth term, 1 over n times natural log of n all squared, what I have there is I have a product of two things raised to a power. So I can apply the rule for exponents that says when you have a product raised to a power, you can apply that power to both of the factors in the product. So I can apply the square to the n squared and the natural log of n. And as soon as I do that, as soon as I pick up on that n squared in my denominator, that's making me think, hey, I could make a comparison to a p-series with p equal 2, which would be convergent. I just need to make the argument that this is less than, so I'm going to put a question mark here, okay, because this part is a little less than obvious. Okay, I need to be able to make an argument that this is less than 1 over n squared. Okay, but I'm going to have to think about this a little bit. If I drop natural log of n out of the denominator, will that make the denominator smaller? Because that's what it would take to make the fraction bigger. Okay, it would help if I thought about what natural log of n looks like. Now, n starts at 2, so let's kind of use that in our analysis. Sometimes it helps to kind of write out the first few values to see what's going on. So I'm going to write out a few values of n and compute their natural logs. Okay, so when n is 2, I would get natural log of 2. Okay, so natural log of 2, according to my calculator, is 0.69 roughly. So let's write that down. 0.69. Change that 2 to a 3. I get 1.09, and it keeps going. And change that 3 to a 4. 1.38, and it keeps going. That kept going too. And one more, just for establishing a pattern. 1.6 and 0, and it keeps going. Okay, you can see that the values are getting bigger. Okay, I think you already know that natural log is an increasing function, so that's no big surprise. Okay, now here's the thing. As long as what we remove from the denominator is bigger than 1, then it will be true that when we pull it out, the denominator gets smaller, and that makes the fraction bigger. However, if what we remove from the denominator is smaller than 1, if I take a factor of 0.69 out of the denominator, and 0.69 squared is actually even smaller, because if you take any number less than 1 and you square it, it's even more less than 1. Okay, so if I take 0.69 squared out of the denominator, that actually makes the denominator bigger, which would make the fraction smaller. So this statement here, that 1 over n squared times natural log of n squared is less than or equal to 1 over n squared, that's actually not true for n equals 2, but it looks like it would be true for all the n values after that. So that's actually good enough. I'll just put this little caveat on here. I'll say that that inequality is true if n is greater than or equal to 3. Now I can erase my question mark. And remember, when we looked at our comparison test, only required that the relationship between the series we're testing and the series whose convergence we know be good for the n values past a certain point. Okay, and in fact that is true in this case. Okay, it's good as long as n is greater than or equal to 3. So in this case, that big N represents a 3 for this particular problem. So we're still covered. We're still good. Okay. Now, we also needed to be a little bit careful because natural log can sometimes yield negative values. But since n is greater than or equal to 1, natural log will also be greater than or equal to 1. Okay, so since n is greater than or equal to 1, natural log of n is, I'm sorry, I said that wrong. Since n is greater than or equal to 1, natural log of n will be greater than or equal to, not 1, 0. Okay, and in fact, n was greater than or equal to 2, so we can say natural log of n is strictly greater than 0. Now the reason I have to be careful about that is because natural log can have a negative value without having a negative in front of it. But that's not going to happen to us here. So 1 over n times natural log of n all squared has got to be greater than or equal to 0. Okay, so let's kind of wrap all this up. We'll say since our nth term of our sequence, 1 over n times natural log of n, quantity squared, is greater than or equal to 0, but less than or equal to the nth term of a convergent p-series for n greater than or equal to 3, which is good enough. Now I need to explicitly acknowledge the series 1 over n squared is a convergent p-series. Alright, that's all the conditions. So since all of this is true, we can say by the comparison test, by the comparison test, our series where n goes from 2 to infinity and the nth term is 1 over n, natural log of n, denominator squared, is convergent. Alright, that takes care of this problem. Now, let's do some problems that are going to make use of the second part of the comparison test. Okay, we haven't made use of this yet, but this is for showing that a series is divergent by showing that its terms are bigger than the terms of a series that we already know is divergent. Okay, so again, this is going to be making use of series whose divergence we can tell easily, p-series and geometric series usually. Okay, but this time we have to argue the other way. We have to show that the terms of the series we're testing are bigger than or equal to the terms of our known divergent series. And it still needs to be the case that everything is non-negative. Alright, let's have a look at this problem. We want to determine whether or not the infinite series whose nth term is n plus 1 over n squared is convergent or divergent. Okay, now I've already kind of told you that at this point we're going to pivot from problems that turn out to be convergent to problems that turn out to be divergent. But let me tell you how you would kind of know what's going on with this one right off the bat. First things first, I would try to analyze, is this like a p-series or like a geometric series? Since my powers are constants and my bases are n's, that would tell me this is kind of like a p-series. Now to figure out what p-series I'm going to compare to, I'm going to focus on the leading terms or the highest degree terms of the top and bottom. Okay, the n and the n squared. Okay, focusing on those, I can see that the top has a degree of 1, the bottom has a degree of 2. That's a difference of 1. So that tells me that I'm going to wind up comparing this to a p-series where p is 1. That's convergent. I'm sorry, I said that completely wrong. That's divergent. So I want to try to make an argument that this is bigger than the terms of that divergent p-series. So I'm going to take my nth term and I'm going to try to make changes to it that make it smaller. So if I drop plus 1 out of the numerator, that makes the numerator smaller, that makes the fraction smaller. But then n over n squared is of course the same thing as 1 over n, and 1 over n is the nth term of a divergent p-series. So really, I have less to do here. Okay, since I have less to write on this one, since the series whose nth term is 1 over n is a divergent p-series. Okay, now I still need to verify that my nth term of whichever series is smaller. Okay, so in this case it'll actually be the p-series that I'm checking out. Okay, I need to confirm that that is smaller. So since this is a divergent p-series and 1 over n is in fact greater than or equal to 0 for n greater than or equal to 1, we've already established that our nth term is bigger than or equal to the nth term of our divergent p-series. We can again use the comparison test. So by the comparison test, our original series that we were testing, our series where the nth term is n plus 1 over n squared, is divergent. Now, I haven't been doing this, but what we just did was we finished a proof. A lot of times a symbol that we use to signify we've reached the end of a proof is to write a little square and shade it in. So I think maybe I'll start doing that just as a way of kind of showing the problem is now capped off. And that's all there is for that one. Now, I put something in the outline. I don't know if the book ever directly addresses this. It might just assume you know it, but I felt like at some point it needed to be addressed. It's a consequence of theorems we looked at earlier, but I don't know that we ever quite put it all together. So I'm just going to state it. If you multiply all the terms of a series by the same non-zero constant, that doesn't change whether the series converges or diverges. So, for example, if I look at a series like a series where the nth term is 1 over 2n, I can immediately rewrite that as a series where the nth term is 1/2 times 1 over n. Okay, but now I can kind of ignore the 1/2 since it's a constant multiplier and say, hey, without the 1/2, this is clearly a divergent p-series. So multiplying a divergent series by the same constant in every term, as long as it's not 0, not going to keep it from being divergent. So this one is divergent. Okay, and that's honestly something you're kind of supposed to be able to just see, that constant multiplier doesn't affect your answer. This is still a divergent p-series even with that constant multiplier. And I bring that up because that's going to be relevant in the next couple of problems we look at. So let's look at problem 197. Alright, here's problem 197 from the book. Still doing the same basic thing. The problem is still use the comparison test to either show that it's convergent or show that it's divergent. Now again, the first thing I'm going to do is I'm going to try to decide, should I be comparing this to a p-series or to a geometric series, seeing that n is a base and not showing up as a power anywhere, my first thought is this is kind of like a p-series, and since the only power of n I'm seeing is an n to the 1, I'm thinking, yeah, this is like the p-series where n equals 1, which is divergent. So that means I need to make an argument, if I can, that these terms are bigger than the terms of that p-series, okay, or of some p-series that's divergent. So I'm going to take my nth term, and I'm going to try to make changes to it that make it smaller. So let me see, if I drop out this minus 1, dropping out the minus 1 would make the denominator bigger, and that makes the fraction smaller. So if I drop that out, I can say, yeah, 1 over 2n minus 1 is greater than or equal to 1 over 2n. Okay, but 1 over 2n is just 1/2 times n. So it's just a constant multiple of the nth term of a divergent p-series. Okay, so I'll say it like this. Since the series whose nth term is 1 over n is a divergent p-series, the series whose nth term is 1 over 2n is also divergent, and 1 over 2n is greater than 0 for all n greater than or equal to 1. And then since 1 over 2n minus 1 is greater than the nth term of a divergent series, we can use the comparison test. So, since that's true, by the comparison test, our series whose nth term is 1 over 2n minus 1 is divergent. Bada boom, and that's all there is to 197. Let's do 196. Alright, here's 196. Okay, it's an infinite series where the nth term is 1 over 2 times n plus 1. Now, I gotta tell you, right off the bat, I'm thinking this one is just like the last one, because the only thing I'm seeing with an n is an n to the 1, and that's in the denominator. So I'm immediately thinking this is probably like the p-series where n is 1. This is probably divergent. Okay, so let's see if we can make the argument. I'm going to take my nth term. Might be helpful to simplify that. So just distribute that 2. Okay, 1 over 2n plus 2. Now, I want to be able to make a comparison to either 1 over n or 1 over 2n. Either way, I'd be able to make an argument for divergence. But the only really obvious thing to do is to drop off that plus 2. Okay, now the problem with that is, if I drop off the plus 2, that makes the denominator smaller. But if that makes the denominator smaller, it makes the fraction bigger. So this would be less than or equal to 1 over 2n. Now here's my problem. 1 over 2n is divergent, but if I want to show that this is also divergent with the comparison test, I need this to be the bigger thing. I only want the thing I'm testing to be smaller if I believe it's convergent. If I believe it's divergent, and I still do, if I believe it's divergent, I need it to be bigger than the nth term of a divergent one. Okay. Now, I can still save it, but I got to get a little creative to save it. That's not going to help me. Let's start over. 1 over 2n plus 1. I think it's still best to try to simplify that by distributing that 2. Okay. But let me see. I want to make a change that makes the denominator bigger and therefore makes the fraction smaller. So rather than dropping out the 2, I'm going to replace it with an n. Okay. Now, as long as n is greater than or equal to 2, I just made the denominator bigger. Okay. So that's greater than or equal to this if n is greater than or equal to 2. And it's okay if my inequality only holds for n values past a certain point. Okay. But check out what that just did for me. That equals 1 over 3n, which is 1/3 times 1 over n. Yeah, that's divergent. Okay, so I just showed that my terms are bigger than the terms of a divergent series. So I can still make the argument. Okay, so since 0 is less than or equal to 1 over 3 times 1 over n, and that, by just following back through here, is less than or equal to 1 over 2 times n plus 1. Okay, basically just confirming everything I need to use my comparison test. Although I will say, and the series where the nth term is 1/3 times 1 over n is a divergent p-series. Okay, is a divergent p-series by the comparison test our series, so our original series that we were testing, is divergent because its terms are bigger than the terms of a divergent p-series. Now here's the thing though. You might have thought when I made this little change here where I replaced the 2 with an n so that I could get it to be, I could get the new fraction to be smaller rather than bigger. You might have thought, gosh, that's getting kind of creative. Like, I'm not sure I would have thought of that in the moment. Okay, that is a completely legitimate concern. The fact of the matter is, all the examples we've done so far prior to this one were kind of hand-picked so that when we started dropping things out, the fraction would get smaller if we needed it to get smaller, or get bigger if we needed it to get bigger. Okay, but the reality is that if we haven't hand-picked our examples, we often do have to get creative to make the fraction bigger or smaller, and that can get to be pretty tricky. But it turns out that there's a second theorem in this section that really helps with problems like this one. I used the comparison test, but it actually would have been easier if I had used the second theorem, which is called the limit comparison test. Let's have a look at that. So this is on page 490 of section 5.4. Page 490, the limit comparison test. Okay, this one is actually kind of an easy to apply test. Okay, what we do, now there's 3 different scenarios. I'm going to focus for the moment on just this first one. What we do is we take a sequence limit of a ratio, and what's in that ratio? The nth term of the series that we're testing, and the nth term of a series whose convergence or divergence is already known. And here's what we're looking for. We're looking for that limit to be a number and not 0, a non-zero number. If that limit turns out to be a non-zero number, then the 2 series that we were comparing with this limit comparison test, as opposed to the regular comparison test, those 2 series either both converge or both diverge. So let me show you what that looks like if we apply it to 196. Alright, let's take a second look at 196. We successfully did it with the regular comparison test, but that was kind of tricky. Let's try it with the limit comparison test. Now remember, before I said that the first thing I noticed is that it looks like the only n in this problem is an n to a power of 1 in the denominator. That immediately makes me think that this thing probably behaves like the p-series where p is 1, so it's probably divergent. If you pick up on that it's like a certain p-series, you can do a limit comparison test. So you're just taking a sequence limit, a limit of the nth terms, where you take the nth term of the series you're testing and you divide it by the nth term of the p-series that you believe it's similar to. Now, when I divide by a fraction, that flips the fraction. So that would be equal to the limit as n goes to infinity of, if I flip this one, it just puts my n in the top. And I'll go ahead and multiply out the bottom. 2n plus 2. And of course, we learned previously that if you're taking the limit of a rational expression and the top and bottom have the same degree, then you can just take the ratio of those leading coefficients. And so that limit would just equal 1/2. And 1/2, of course, is not 0. Okay. So we've done most of the work of showing that the conditions of the limit comparison test are justified or satisfied. I just need to basically just confirm that all this stuff is positive. And I can pretty much just say it's positive by inspection. So, since 1 over 2 times n plus 1 is greater than or equal to 0 for n greater than or equal to 1, and 1 over n is greater than or equal to 0 for n greater than 1. And we've already checked that the limit of the ratios of those things is a non-zero constant. That takes care of all the conditions of applying the limit comparison test. So we can say, by the limit comparison test, underline limit, we're not using the regular comparison test, by the limit comparison test. Oh, there is one more thing. By the limit comparison test, the conclusion that I make also depends on knowing whether or not the series whose nth term is 1 over n diverges. So by the limit comparison test, so I'll just kind of toss this in. I should have said it sooner. And considering that the series whose nth term is 1 over n is a divergent p-series, we can conclude so the idea is that if all this stuff is satisfied, the two series we're comparing either both converge or both diverge. So now we can conclude that the series we were testing is divergent. For this particular problem, I like this limit comparison test more than the direct comparison test because I really didn't have to get creative. I mean, pretty much as soon as I realized that this series was similar to this series, I pretty much knew what I needed to do. I just needed to work out the limit and write everything up. Alright, let's apply this to another problem and then talk about the other cases of that limit comparison test, and then I think we'll be in a good place to stop. Alright, So here's the last problem we're going to examine, although we're going to think about it a couple, two, three different ways. Um, in this problem, the book actually comes out and says use the limit comparison test. But let me kind of explain how we would come to that. I'll tell you what I see when I look at this problem. Okay, I see that I've got a base raised to the power of n there. In fact, I've got it a couple times. So that's telling me I should probably be comparing to a geometric series. Okay, now if I take my nth term and I start trying to simplify it, okay, one way to simplify it is just to drop out a term. Okay, so I could drop out that minus 3 to the n and get 1 over 4 to the n. 1 over 4 to the n, it's the same thing as 1 to the n over 4 to the n, since 1 to the n is still 1. And that's the same thing as 1/4 to the n. That right there, that's a convergent geometric series. Convergent because the r value is between 1 and -1. And here's the problem. Okay, when I dropped out that minus 3, that makes the denominator bigger since I dropped out something that was being subtracted. And if I make the denominator bigger, that makes the fraction if I make the denominator bigger, that makes the fraction smaller. Okay, so I've just shown that my terms are bigger than the terms of a convergent series. Okay, which means that if I use the direct comparison test, the directionality is backwards. If I had shown that my terms were smaller than the terms of a convergent series, I'd be able to use the direct comparison test and I'd be home free. Since my terms are bigger than the terms of a convergent series, I can't really draw any conclusions from the direct comparison test. But I still believe that this is probably similar in nature to that. It's still basically a geometric series with an r value of 1/4. Okay, so my next thought is, if I can't use the direct comparison test, I'm going to use a limit comparison test where I compare this to that by taking the limit of the ratio of those things. And as long as that limit comes out to be a non-zero constant, I can conclude that they have the same behavior, convergent or divergent. Now, like I said, the book told me to use the limit comparison test, but I'm trying to help you understand how I would come to that conclusion anyway. So the book never calls it the direct comparison test. It just calls it the comparison test. But the one where we compare magnitudes is no help. Direct comparison test is no help this time. Now maybe I could come up with a creative way to make it helpful, but I gotta tell you, most of the time, if the direct comparison test isn't working out easily, it's usually going to be better to just hop over to the limit comparison. If you know what you should be comparing it to, move on to the limit comparison test. Alright, so I'm going to take the limit as n goes to infinity. Now I'm going to take the nth term of the series that I'm testing, and I'm going to divide it by the nth term of a series that I believe has a similar long-term behavior. Okay, and you know what? I'm going to write it like I'm going to write that as 1 over 4 to the n. So of course that is equal to the limit as n goes to infinity, and I just need to flip that fraction. So that becomes a 4 to the n in the numerator over 4 to the n minus 3 to the n. Alright, now here I can't really use that rule about comparing the degrees, because that really only works when the degrees are constants. Okay, but I can use a little bit of algebra here. I can say that what I'm going to do is I'm going to multiply the top and bottom by 1 over 4 to the n. So let's make that explicit that this is multiplication. So I'm multiplying the top and bottom of this fraction by 1 over 4 to the n. So then this equals the limit as n goes to infinity. Well, 1 over 4 to the n times 4 to the n gives me a 1. So I get a 1 here as well. And then I get a 3 to the n over 4 to the n. Okay, but now I'm going to use that rule that says, hey, if you're dividing and you've got the same power, you can make it one fraction to that power. So this equals the limit as n goes to infinity of 1 over 1 minus 3/4 to the n. Now the reason that's helpful is because now this term, now remember we're taking a sequence limit. This term is a geometric sequence whose r value is between 1 and -1, which means that its limit as n goes to infinity is 0. So the value of this limit is 1 over 1, or just 1, which is not 0. Okay, so the limit comparison test is going to allow me to draw a comparison here. Okay, so here's what I'm going to say. Since the series whose nth term is 1 over 4 to the n is a convergent geometric series, and it's convergent by inspection because the r value is between 1 and -1, is a convergent geometric series, and and what else we need to check? Oh, we need to check that everything's positive, and 1 over 4 to the n is clearly positive. And what? I needed to know that the series I'm testing against has positive terms. Oh, and I need to know that the series I'm testing has positive terms. Okay, so and 1 over 4 to the n minus 3 to the n. Remember, we showed that's greater than 1 over 4 to the n. Okay, take off that minus 3n. That makes the denominator bigger, which makes the fraction smaller. Aha! But we already said that's greater than 0 just by inspection. Alright, that's all the conditions. So we can say by the limit comparison test, our original series is convergent. All right. Now, I did just want to point something out to you. Okay, I won't completely work through the problem again. Okay. All right, so here's a couple of quick notes to kind of finish this off with. One thing you might have wondered is how I knew to compare to 1 over 4 to the n rather than 1 over 3 to the n. The truth of the matter is that I just took the 1 over 4 to the n because 4 to the n was written first. Okay, but it actually would have worked if I had done the limit comparison test with 1 over 3 to the n. So if I take the limit as n goes to infinity of the nth term of my series divided by the nth term of another convergent geometric series, let's see what happens here. I get the limit as n goes to infinity, I got to flip that again, of 3 to the n over 4 to the n minus 3 to the n. Now in this case, I would again multiply by 1 over 3 to the n divided by 1 over 3 to the n. So this would give me the limit as n goes to infinity of 1 over, so that becomes a 1 and that becomes a 1, but this will become a 4/3 to the n minus 1. Now 4/3 is bigger than 1, so this term here represents a divergent geometric series. That term goes to infinity, which means that the limit goes to 0. Now, we've been using the first case of the limit comparison test, which requires that we get an answer that's not 0. But there is actually another case that covers how we might interpret it if the limit is 0. Okay, it's case 2 here. Okay, in case 2, if our limit turns out to be 0, what that means is the bottom must have grown a lot faster than the top. Okay, if the ratio is going to 0, the bottom one must in fact be a lot bigger than the top one. So if the bottom one, the b sub n, converges, we can conclude that the top one converges. And that was the case here. Okay, the bottom one, the one we divided by, was a convergent geometric series. Okay, so it's going to 0, the top's going to 0, but the bottom must be going to 0 faster for the ratio to have come out to be 0. So we can still conclude that since the bottom is converging faster, top must be converging too. Now again, all that would hinge on everything being positive. Okay, both of these comparison tests require that. Now, sometimes you might have it ordered the other way. Okay, so what if I had ordered it the other way? With the 1 over 4 to the n, it wouldn't have actually changed our conclusion. We would have gotten a limit of 2 instead of 1/2. But with this one, it makes a difference. So let's just say, for the sake of argument, that I had ordered it differently. So 1 over 3 to the n divided by 1 over 4 to the n minus 3 to the n. So, I mean, if we had put it in this order, then this would be the fraction that would get flipped. So I would have the limit as n goes to infinity of 4 to the n minus 3 to the n over 3 to the n. I would still wind up multiplying top and bottom by 1 over 3 to the n. I would want to drive as many things to 1 as I could. But when I do that, my limit, as n goes to infinity, this becomes the limit of 4/3 to the n minus 1 over 1. So remember, we said 4/3 to the n is going to infinity, so our limit would become infinity. Okay, well, if our limit is going to infinity, that's actually the third case of the limit comparison test. So if the limit is going to infinity and the bottom one diverges, then the top one diverges. Well, you know what? In this case, I don't know that the bottom one diverges. That's the one I'm wanting to test. So, you know what? It looks like I would want to just never set it up that way. Okay. And so I'll let that be the point. It is actually possible to draw a conclusion. I think I probably could have had a better example for this. It is possible to draw a conclusion when the limit is infinity. Okay, but the conclusion would have to be that if the bottom one is divergent and the limit still went to infinity, that the top one must be growing even faster. Okay, so that could be used to show divergence. But in this case, it's not really telling me anything. But I'll tell you one thing that you can get as a takeaway from this is you should always put the series whose convergence or divergence is known on the bottom. Okay. Alright. Well, I think I'm going to cut it off there. We've covered everything we needed to cover in this section. So I'm going to go ahead and call it a night. You could probably tell that it was starting to get dark on me. I had to flip the light on. But that's it for section 5.4. As always, let me know if you have any questions. We'll go over some problems together. Take care, everybody. Stay safe and stay healthy.